Good morning, everyone. We are Group 5. I am Xander Craner.
I'm Stanley Zhang.
I'm Jeffrey Perez.
And today we will be explaining what happens when we try to make a dagger out of aluminum and steel by cold working, using the same metals we used in our tensile and hardness experiments. Let's start with the setup. We'll simplify the dagger shape to a cylindrical rod. The original rod has a diameter of 5 centimeters, and we're going to reduce it down to 3 centimeters by cold working. For example, through drawing or forging. Drawing being forcing through a smaller hole over and over, or forging by simply just hitting it with a hammer over and over. The amount of cold work is based on the reduction in cross-sectional area. The initial area is found by A0 equals pi times 5 squared over 4 equaling 19.6 centimeters squared, and the final area, AF, is found by pi times 3 squared over 4 equals 7.07 centimeters squared. So the percent reduction in area, our cold work, is CW equals initial area minus final area all over initial area equals 64%. And each of those equations is simply just a plug-and-play version of the area for a circle. That's a 64% reduction in area, or a true strain of about 1.02. That's actually quite a lot of plastic deformation.
Now let's talk about the steel dagger first. In its annealed or normalized condition, many steels have a tensile strength between 400 and 600 megapascal, and an elongation between 15 and 30%. After 64% of cold work, the steel's dislocation density increases dramatically. This makes it much harder and stronger, typically increasing the tensile strength to somewhere between 750 and 1100 megapascal. However, the downside is that ductility drops, often down to 5 to 12%. So if our design goal is ductility above 15% and strength about 800 megapascal, we'll meet the strength but not the ductility. To get both, we need to either use a more advanced alloy or apply a partial annealing or tempering heat treatment after cold work. Now, let's look at aluminum under the same process. Aluminum starts off much softer. For example, an annealed 6061 aluminum alloy might have a tensile strength around 200 megapascal. If we apply the same 64% cold work, aluminum also hardens, but not nearly as much as steel does. That's because aluminum has a high stacking fault energy, which allows dislocation to rearrange and partially recover during deformation. So after the same process, aluminum's tensile strength might only rise to about 240 to 320 megapascal, and its ductility drops to just a few percent. In other words, the aluminum dagger becomes stiffer and harder, but not extremely strong, and quite brittle.
So let's talk about the microscopic mechanisms of cold work, or what happens on a more atomic scale. When we cold work a metal, there's a big difference between cold working and working on a metal usually. So cold work is usually what you do when you take any piece of metal and you change how the shape is at room temperature. In most scenarios, like your wires, like all of those, they're all being pushed through very, very high temperatures, and then they're being molded into different shapes. Or in some cases, like if you're making a spoon, it's going to be a very, very high molten metal being poured into a cast and then trimmed down afterwards. Cold work, on the other hand, is taking something like that same spoon and you're just hitting it over and over again to create a ball, which if you do that, cold working makes it a lot stronger, and these are the reasons why. Dislocations in cold worked steel or cold worked metals multiply and tangle, which block each other's movement, and when it blocks each other's movement on an atomic scale, if you have two atoms that were around here back then, and now they're right next to each other blocking each other's movement, there's going to be a lot more stress needed to move anything or deform the shape at all, which is why strength and hardness increase. Now, if you look at the grains of atoms, not exactly grains, but like if you have steel, there's going to be many different parts, which are all molecules combined. Those are what's considered grains. The grains will elongate and form subgrains, sometimes splitting. And due to this, the structure becomes distorted, which stores a lot of strain energy. And this strain energy is something that both makes it a lot stronger, but it also makes it a lot more brittle, because when you have high strain, at the peak strain on a stress strain curve, there's always going to be that moment when you get a little bit higher and then you go all the way down, reaching plastic deformation. So beating something and making it into a cold work steel, it takes it to that peak and gets it right before the plastic deformation, where it would be too brittle and just break off. For steel, on the other hand, which has a lower stacking fall energy, dislocations are less mobile, so they pile up. So in our experiment, we realized that steel could stretch out a lot more than aluminum, where aluminum, when you pulled it, it snapped almost instantly. Steel, you could stretch it out for a long time, which led to it being able to be pulled and then finally giving out and being plastic. Now, because of this, dislocations are less mobile, so they pile up on each other, which makes it so that it's a lot stronger in work hardening. And going back to aluminum, on the other hand, dislocations can move and rearrange a lot more easily. So in our test, when we pulled them apart, the aluminum just snapped right off. It means that it recovers dynamically, so it increases the strength for smaller and same amount of cold work. So the amount of work that's being done for steel and aluminum, if they have the same amount of work being done, steel is gonna have a lot more hardening, and aluminum's going to have a lot less hardening and even break at some points. Now, if we look at the effects on the properties of these two materials due to this, hardness increases with cold work because dislocation density increases, and this just means that the hardness increases. And as such, because of the hardness increasing, the tensile strength would also increase, because hardness and tensile strength usually go hand in hand. But because of this, the ductility, which is the brittleness, decreases, because the material can no longer sustain much plastic deformation before fracturing. And under the microscope, fracture surfaces change from large, deep dimples, which show high ductility, to small and shallow dimples, or even brittle-looking features in the heavily cold work samples. So if you have the aluminum or the cold form steel, or cold work steel on the other hand, when we were pulling it apart, you could feel little bumps that started to show up on the steel, whereas on the aluminum, you have a lot less of those ridges. They're still there, but steel had a lot more of the little fractures and ridges as you pulled it more and more. And now for the summary. So this is just a really quick graph of what exactly happens in everything that we do. So this is the properties, which are tensile strength, ductility, and hardness. Tensile strength and hardness kind of go hand in hand. And ductility, on the other hand, is something else completely. It's how brittle it is. Tensile strength is how much you can pull it. And hardness is just how hard the material is in general. And if we look at the steel and aluminum after 64% cold working, the tensile strength for steel increased by a lot more than the aluminum, almost triple as much. However, the ductility only increased a little bit. Well, looking at it here, it only increased a little bit, but percentage-wise, 3% is a lot more than, or a 3% increase in steel compared to aluminum is a lot more than what it seems. And finally, the hardness, where it increases a lot more sharp than the aluminum. And so finally, due to all of this, you can tell that steel hardens more while aluminum recovers more during deformations and cold working. So for some final thoughts, if our goal in the end is to make a stronger but still ductile dagger, for steel we can achieve both strength and reasonable ductility through cold work, followed by controlled heating. So if you look at diamonds, for example, diamonds are made under a lot of high temperature and high pressure. Obviously not high pressure for steel, but because it's under a lot of temperature, it's going to become more brittle, which is why diamonds shatter. For aluminum, it's better to rely on age hardening if we want higher strength, which is just having it age and like grow strength as we increase it. And that's about it. But in short, cold work hardening increases strength and hardness but decreases ductility. And steel benefits a lot more from cold working than aluminum because of its lower recovery rate and higher strain hardening capacity. Thank you.